Well, welcome everybody to another online class for multivariable calculus. Um, so this week we're continuing to look at vector calculus. So looking at two things. So the first two is curl and divergence, which are the how to differentiate vector fields, or two different ways of differentiating vector fields. And then we'll look at flux, or actually more generally surface and flux integrals, really. So I want to try to get an intuitive understanding of these things if possible, and then we'll look at the formulas as well. So in terms of assessment coming forward, you've got assignment 3 coming up soon. So assignment 3 has question 1, which is a bunch of line integrals. So that's what we looked at last week. And so using things like Green's theorem, fundamental theorem of calculus, fundamental theorem of line integrals, be really good. If those don't work, fall back to parameterization. So that's question 1. Question 2 is about finding curl and divergence, which is what I'm going to mention today. Question 3 is worth 0, so it's not, you don't submit it. Please do not submit it. But it'd be good just to do it for your own practice. And they're just flux integrals. And so, although those aren't worth any marks, there is fourth assignment, a bit more on flux integrals. And that's an online assignment, and you've got that it's open in the last week. And so, knowing how to do flux integrals, more importantly, also knowing the divergence and Stokes theorem, which I'll look at next week, be really helpful for those questions. But I guess the idea is make sure you get assignment 3 ready soon, and by doing so, practice the curl and divergence. So let's dive into today. And again, if you've got any questions, fire away. So first thing we'll look at is the two different ways of differentiating vector fields. So one's called curl, and it's good just to talk about it in general terms first. So curl is essentially a measure of how much a vector field rotates. It's a few things. It's really important. Curl is a vector, so it's a vector. So you apply. It's a way of differentiating vectors, and it produces another vector. So, and people often don't forget it's a vector, so they like to write a single number. It's not. It's a whole vector. So being a vector, the direction of it tells you how, the direction of the spin. So it's the axis of rotation technically, and it works by the right-hand rule. So if I've got an axis of rotation, so the curl would be a vector sticking like this. Then how it works is the right-hand rule, and so you can just get your right hand. This is my right hand with my thumb up in the air, so with a thumb up sign, and I got my fingers here. Then if you put your thumb in the direction of the curl vector, then the rotation is determined by how your fingers go around. So essentially, if you look at your fingers, that means that would be anti-clockwise around the vector. So curl, and like this is true for lots of other orientations too. So the curl is a sort of rotation sort of vector. It tells you the axis of rotation, and it spins anti-clockwise around it, or using the right-hand rule. That's easier to remember. The magnitude of it tells you how much it rotates. Now there's a formula for it, which is written down there. I'll show you a more pragmatic way of working it out. And so that's the actual formula, just there. In practice, a good mnemonic way of trying to remember how to do it is in terms of a cross product, but I'll show you that in practice. So before we get to that, let's just try to do some intuitively. So I've got two different vector fields, so G and F, and they're both 3D, so we'll consider them both 3D. And what I want to do is just to get a sense what the curl is intuitively, and then I'll use a formula to work it out. Might be better just do them separately. Oops. Okay. So what I'm going to do is I'm going to draw the uh, x and y axis for the moment. Um, this, although it's a function, it's a vector. It's got an x, y, and so it's got three components to it, and it's valued for all z's as well. You can see that this vector field is actually independent of z. So there is a third dimension up here of z, but the thing would be the same for all of them. So I'm really just going to draw what the vector field looks like just in the xy plane, and it would be the same in all dimensions. There's a depth to it. And I picked a vector field which is a bit easier to draw to start with. So I'm going to draw it, and I've got a sense of what curl is. If you pick, when y is 0, so pick a few points here, then the resulting vector is 0, nothing at all. So it's 0. Let's pick over here. So let's pick this point here. That will be x equals 2, for example, y equals 1. Then if you plug it in this formula, then the only thing that makes sense is you get a y equals 1, and then so it's y in the I direction, which means the positive x-axis. So you get a little arrow pointing that way. And if you plugged in x equals 1, y equals 1, you get a similar sort of vector pointing that way. Whereas if you go up to x equals 2, y equals 2, subbing in this form, you get 2i, so it's a vector pointing in the y-axis, in the direction of the x-axis, but twice as long before. So that's sort of what it looks like in that way. If you go other places, you get these sort of vectors. And if you go below, so if you did x equals 2, y equals minus 1, you see the arrow goes in the negative I direction. So it goes backwards. So that's approximately what the vector field looks like. So how to work out curl intuitively? So the way to work out curl intuitively is imagine you put a leaf or a spin wheel or something like that somewhere, just throw it in, and you imagine this is a big bit of water flowing. So you can imagine, so if it's a flat, you can just think a leaf. In this case, it's three-dimensional, right? So you imagine put a ball in. How does the ball spin? How is it spinning? So when you put this ball in, is it going to spin at all? So if it doesn't spin, it would imply no curl. If it does spin, it tells you it's got a curl. So if you just think about it, so it's flowing in the same way for all different z values. So you don't have to write the z value. That's constant. But if you think about it here, then the whole ball would be pushed along in that direction. So there'll be a net push. So it would actually move. But more than that, it's going to move faster at the top than it is at the bottom. So because it's moving faster at the top will move quicker than the bottom, and so it'll actually spin around. So this ball, apart from moving, will also spin around as it goes through. And again, if I picked any other pot, put a ball down the bottom here too, it'll be pushed. It'll go the opposite direction, but it'll be pushed more at the bottom than the top, so it will still spin around. And you can see in both cases, it's still spinning the same direction. So if I pull out my right hand and and put it in the sort of a shape of the thumbs up, and you have to again do this to yourself. You can't quite see I've got a video of my hand here, and you just let your fingers curl in that direction of that spiral. Then the thumb tells you which way it's going. So let's see if so if you curl my right fingers, it's my fingers in that same sort of direction, then my thumb is pointing into the page or into that direction. Yeah, that's right. And so the curl would be into the page. Oh, I've got to remember this stuff. Yep, in the page, which would be in the negative k direction. And let's make sure. So that's negative k direction. That's what the direction. We don't know what the magnitude is, so we can't see from the picture just how much it's spinning, admittedly. So it could be spinning really fast or really slow. So it's proportional to this, um, but it's always pointing into the page. So it's at least that direction. So everyone okay with that? So that's just intuitively. So curl is just a measure of how much it rotates, and the direction of the curl is the axis of rotation. And you really work it out intuitively, at least, by using this right hand rule. So pull out your right hand, it tells you which way to go. So in how you work it out analytically, which is what you need in your assignment at least, is the actual curl of a vector field, so G in this case, is mnemonically, so a way of remembering it, is doing a cross product of the differential operator Nambla and G. So let's write in a few things. So Nambla here is just short for the vector consisting of partial with respect to x, partial y, partial z. So it's I, j, k component, or you write the vector. So that's what it stands for. So the way to work out a curl then, it's a cross product. So how you work out how I write down cross products is I've got is it a determinant? Again, just a way of remembering it. It's just a so there's the three components I, j, k, and it's useful to have these placeholders for the three components. That's often how it's, well, at least I find it easier to cross product. Then you write down the components of the first vector, which happen to be a differential operator in this case. So these different partial derivatives. Now for short, I often just write partial x, partial y, partial z sometimes, which really do stand for the full operators, just the different operators. And then I write down the components of G. So G in this case, the I component is y, the J component's nothing, the K component's nothing. So that is the vector G there. And this is just a normal way of remembering how to do cross products, and then just say to do the cross product. So the way to do cross product, so the way I remember it, there are two common ways of doing determinants 3 by 3, but the way I remember to do determinants is just moving along the top row. So you got I, so the I component, is you put your, cover up the row and column it contains, and then do determinant of what's left. So you get, the partial derivative of 0 respect to y minus the partial derivative of z respect of 0. So I'm just basically doing that determinant there. So partial y of 0 minus partial z of 0, which is going to be 0 I, of course. Then I do the next component. So go along. And as you're going along, you alternate signs. So it's minus something or other times by j. So with j, again, going to determine what's left over. So I do del partial x of 0 minus partial z of y. What's that equal to? So you do so the partial derivative of 0 respect to x gives you nothing. Partial derivative of z of y respect to z gives you what, guys? Zero, absolutely. So if you add them all up, you're getting minus or plus 0j. So not much so far. And so the last case we're going to do is the K1. And again, it's an alternating sign, so positive, negative, positive. And so the K1, you do the partial derivative, you do the determinant what's left over. So it would be the partial derivative of x of 0 minus the partial derivative with respect to y of y. So what's that equal to? Yep. And so that's going to be equal to minus 1. And so we get minus 1 times by k. And so you can see that if you keep simplifying, in the end, the curl is actually equal to minus k. which is what we guessed. So we could, from our picture, we could work out it was in the direction of minus k. We couldn't work out the magnitude just from the picture alone, but you can see just it's identically equal to it. So that's how you work at curl. And a few things to remember, it's a vector. So you can write like this. You could alternatively write it as 0, 0 minus 1. That's also fine. It could be a function. So in general, it's a vector field. It happens to be fixed in this case, but it could be variable on x, y, and z. So in general, the curl of a vector field is another vector field. And so some people just write down minus 1. That's not quite right. Now, there are things such as a 2D curl. I think it's just best always just write down 3D curls. I think that's always a helpful way of remembering it, and always think of things being embedded in 3D. So whenever I write down curl, I'm always thinking about the 3D version of it. So that's the curl in this case. So let's do another one. This is another vector field. So I'll write the axes more standard this way. So x, y, z. This is a form of Hooke's. This is a bit of physics. This is sort of Hooke's law, and so this is a force field. We've got a particle in the middle, completely surrounded by an elastic medium. So if you push it in any direction, the elastic material just bumps it back towards the origin. That's basically it. The force is always pushing back towards the middle. This sort of formula you see for springs if you've done physics, but it doesn't matter. So if you just quickly draw the force, so x, y, z is just location. So if you pick any point, x, y, z pretty much is so minus x, y, z just is a vector pointing back towards the origin. So you pick anything in 3D space. The vector is always pointing back towards the origin, and the magnitude of it, the length of it, is just how far away from the origin it is. So that's sort of what the vector field looks like. So again, if we chuck a ball in 3D space to think about how much this is spinning, and you can see that if you put the ball anywhere, it's going to move towards the origin. That's what this force field's doing, just pushes everything towards the origin. But you can see that on both sides of the ball, it's pushing the same amount, the same magnitude. And so it doesn't create any spin to it at all. And so the curl of this, by the look of it, it's going to be 0. So it doesn't look like there's any rotation happening at all. And you can check that out, and so you can verify that. So that's the intuitive understanding. So you can do that explicitly. So the curl, again, is cross product. I, j, k of the partial differential operators of the vector field. So minus x, minus y, minus z. So if you do the I bit, that'd be del y of minus z and del z of minus y. So the partial derivative with respect to y of minus z, which is 0, minus the partial derivative of z partial derivative of minus y with respect to z. That's the I component. So just doing that cross product, that determinant there. With j, it's a big minus sign. Well, it matters so far, but it's important to remember it in there in general. Again, deuce to the determinant of that cross. So the AD minus BC formula. So del x of minus z minus del z of minus x. That's the j component. And again, and the last one for the k one, it's alternating sign. So in this case, it's positive k. And again, you do that AD minus BC formula. So del x of minus y minus del y of minus x. And every single situation, you're doing lots of different partial derivatives, but every single time the letters don't match up. And since the letters don't match up, you're going to get 0 in every single case. And so you're going to get the 0 vector. So I write, see res vector for short with 0, little squill underneath it, or I could write it as 0, 0, 0. So it's not the number 0, it's a vector 0. And so that therefore, as we could see from the picture, there is no rotating at all. So the vector field doesn't rotate. So just something special. If you if the curl is 0 everywhere, so if the curl is identically 0, then that tells you that F is a conservative vector field. So a 3D, so this is what you use in 3D in general, and then so just remember from last week, I should say, that means that it can be written as the gradient vector of some function, the gradient of some function, and so in this particular case, this is Hooke's law that capital F can be written in terms of minus the gradient of half the length of the vector squared. And that's the potential function. So if you take the negative of that, so positive, so you take the positive of that, so the negative sign of that, so you get half the length of x squared. That's called the potential energy that corresponds to the function. So this is the sort of formula that you'd see for the potential energy of a spring. So again, I don't know how much physics you did. Normally Hooke's law has a constant of k in here. You'd see a k there too. So Hooke springs is another example of a conservative force that you might have encountered in physics. So just showing it, these sort of things cropping up again. So in terms of what you need to know, you don't need to know heaps of physics for this subject. It's good just to see some applications for it. But it's a good way of checking if things are conservative. Just take the curl. And if it is, then and the way to work it out, so the way to actually find this potential energy or the potential function, which is minus sign, really is the same process before we did last week. And that is just go, well, I now know that minus x is equal to the partial derivative of this mystery function f with respect to x. Integrate, that gives you a part of it, plug in the next equation, etc. Keep going until you resolve all the constants. I can do that later if you're curious, but otherwise I'll just push on. So that's the first differential operator, so that's curl. And as I said, it's a measure of how much things rotate. And you can see one uses in terms of if things are conservative or not. Next one is called divergence. So the divergence is another differential operator. It's another way of differentiating a vector field. It's a measure of how the net flow at a point. It's a number. So it's not a vector anymore. It's a number. Positive, negative, 0, etc. So zero divergence means that the amount of flowing into the point and the amount of flowing out of the point is the same. So vector, and again, I think divergence is often a good way of thinking for water flowing around a place. So no flow in, no flow out. Positive divergence, it's called a source for short. Pretty much the amount of it's more flowing out than flowing in. A negative divergence means it's called a sink. So there's more flowing in than there are out. So they're collecting stuff, so to speak. And you can imagine that. So for water flowing, it shouldn't actually increase or decrease mass. So conservation of mass would imply that in a normal river situation, you have zero divergence. And so if you don't have zero divergence, it means you really have either a leak in your system. So that's why the word sink, which is maybe what you're curious, or a way of adding it to a source. So sometimes that's important to think about, but so zero divergence is a quite natural concept. So, and the way to work it out, it's a bit easier. It can be thought of as the dot product of the partial differential operators with the vector itself, or can be written in short, as you can see there. So it's easier to work out than the curl analytically. So let's go back to our pictures. So this is our picture from before. Instead of working out the curl, let's work out the divergence. So with divergence, is you consider any point at all, just a little box around it, and I want to consider how much is flowing in and out of a little point. So you can see in this point, I've got a lot flowing in, so a big arrow flowing in, and a small amount flowing out. So I've got more flowing in than flowing out, and so it's collecting stuff, so to speak. And so there's a net flow in, and so if you look at my thing, so net flow, so there's more, so there's more flowing in than out, so out's less than in, so therefore we expect the divergence to be negative. How negative? Can't tell from the picture, but at least we've got that intuitive understanding. So as I said, divergence is the measure of net flow. There's more flowing in than out. So everything seems to be collecting stuff. So Hooke's law is a good way of describing force, but it is not a really good way of describing how water will flow around. Water doesn't keep collecting points all the place like that. It just doesn't work. So this is not really a good example of a river flow. It's an example of everything being a source. It's really a sense of a fluid coming together and getting more and more dense as it gets closer and closer to the origin. So it's being more of a compressible liquid, perhaps, is one way of modeling it. As I said, it's much better in terms of physics. But anyway, let's work it out in practice. So the divergence of this, and a good way of remembering, I think, is just take the dot product of the partial differential operators. And dot product just means take the partial derivative with respect to x, the first bit, so minus x up here, plus the partial derivative of the second bit, plus the partial derivative of the third part. And it's always in respect to the corresponding variable. So you guys can do a little bit of work here. So what's the answer? So that's the partial derivative of minus x with respect to x, partial derivative of minus y with respect to y, partial derivative of minus z with respect to z. What's the final answer? So it's minus 3. So each partial derivative would give you minus 1. There's 3 of them. So the answer is total minus 1, minus 1, minus 1 gives you minus 3 as our final answer. And it's negative, like we thought it to be. Just confirming what we've got here. So that's and so we'll utilize divergence in terms of a divergence theorem later on. For example, it's useful there. So let's go to this other vector field we've got. Let's just try the divergence in this case, get a sense of what else you can do with it. So just rubbing out stuff here. As you can see them. Okay, that's good, close enough. So again, what we do is we consider a box somewhere, and we want to consider how much is flowing in and out. So you can see in this case, the arrow coming in and the arrow going out have the same length. They both have length 2, as I described it earlier. So the flow in and flow out are exactly identical to each other. And so the net flow is 0. And so we expect the divergence, at least with that box I drew, will be 0. But if we did the box anywhere else, if it had looked at any other place, it's the same sort of thing happening. The flow in, the flow out ends up being the same. So we can prove that. So let's do the divergence of G. And I say that's the dot product of the differential operators with G. So that's the partial derivative of x with respect to the first component, which is y, plus the partial derivative with respect to y of the second component, partial derivative with respect to z of the third component. Now, y to 0, so that's pretty easy. These variables don't match up. Everything else is 0, so you're getting 0 divergence, just like we thought intuitively. So that's just trying to give you a sense of what they are. And as I said, so since there is no divergence, then this is a possible way of how water can flow. So you're not losing or gaining mass anywhere. It's just moving around a place. And so you're getting if you throw things in, you're getting vortexes all over the place. But so it's physically valid sort of thing to consider. So as I said, we'll use divergence in terms of our divergence theorem later. So it's useful for working out flux integrals in particular. And we'll do Stokes' theorem uses the curl. And that's a way of looking at circulation integrals in particular. So actually, as a matter of fact, we have actually seen curl already. So the curl is seen. So if you did the curl of vector P Q0, which is I, really if you just think of it being 2D, then you end up getting 0, 0, and Qx minus Py. And this expression, Qx minus Py, we've seen, for example, in Green's theorem. It appears in Green's theorem. And also it's a way of checking if the function's conservative or not. And so the curl is actually a part of Green's theorem, and we'll see that in a greater sense when we do Stokes' theorem next week. So that's just a sort of intuitive understanding for those sort of things. So now I've mentioned that, you can go away, do some more practice, of course, but that allows you to finish off assignment 3 in terms of the stuff that's worth marks and put it in. So next thing I want to do is look at the idea of flux. So last week we looked at line integrals. So there are two types of line integrals: scalar line integrals and vector line integrals. So I want to look at the same sort of thing, not for curves, but for surfaces. And so we're going to look at scalar and vector surface integrals. That's the basic idea. So a scalar surface integral is just called surface integral. A vector surface integral is tend to call a flux integral, and it's just a measure of how much flux there, how much things flow. And in terms of what we're concerned about, in practice, we tend to be more interested in flux integral. So, in terms of fields, in terms of things flowing around the place, then ends up being flux integrals end up being a more common application for stuff, certainly in sort of physical and fluid dynamic situations. So that's what I'm going to focus on, something more the flux integrals. So I want to get a sense for what it is. So how would I just jump to an example and I'll talk about some aspects to it. So I've got a picture here somewhere. Where did it go? Come on. Maybe that worked. Oh well, I was trying to get a picture from earlier and it's just failing to work. Hold on, why don't I just... Why don't I use the old cut and paste? That would be better. Okay, so this is my, after all that mucking around, this is my vector field. This is what I've drawn earlier. So this is the one that everything's attracted towards the center. So this is the one that had no curl, but divergence of -3. That's the one we worked out earlier. Let's draw a rectangle in 3D space. So it's a rectangle. It goes length 2 in the x direction, 3 in the y direction. That's my little rectangle here. And it happens to be at z equals 4. So that's my rectangle up here. So x is between 0 and 2, y is 0 and 3, and z equals 4. So I've got my rectangle here. I want to know how much of this vector field flows through the rectangle. So that's what flux is. So flux is how much of the vector field flows through a particular surface. Now, if you look at the surface, there's sort of two ways you can flow through it. You can either flow through it down through a rectangle or up through the rectangle. And there's sort of two choices. You go, well, which one do I pick? And so the way which way we pick is called the orientation. So if you think about it, so for every point on my surface here, if I look at smooth, I've got a normal. So normal is something that's perpendicular. So either you're pointing up or pointing down. So they're my two choices. So I've got two options, are both perpendicular to it. So there are two different normals to it. So an orientation is just picking which side all the normals point. So in this case, I'm going to make sure that's orientated up. That's just my choice. The normal, which I'll draw a picture of, is up. So in this case, it's in the parallel to the z-axis, and so it's pointing up. So it's going to be K. Now I just some letters. I use little n to always refer to the unit normal. So it's a normal of length 1. If I have normals which don't have length 1, I'll use capital N. I will use it later on. Okay, so that's the unit normal. So the flux is how much this vector field is flowing in through this surface. So more precisely, how much of it's flowing perpendicularly through this surface in the direction of the normal. So you look at this picture, all the arrows here are going down at this point in time, in the opposite direction to the normal. Now, since there's quite a bit of flowing through, some are sort of flowing at a slight angle. So when they're flowing at an angle, it's only the perpendicular component that really matters. But still, there's something that's been flowing through. And so if you're trying to visualize it, just imagine it being lots of water, right? So all this water really being sucked into the point. Or it's a compressible liquid. It's all this liquid being compressed into this single point at the beginning here. So it's getting pressed as it goes further in. So you can see as it's flowing through this stuff, there is a lot of flowing through, but it's flowing the opposite direction to the normal. So the flux then would be this. There is something sort of flowing, definitely flow through, but it's in the opposite direction, so it'd be a negative number. Well, that's about as good as we can say for the moment. We'll work on it more accurately in a second. So that's something we'll try to do. So let's just look at some formulas. So before we work out the formula for that, let's go back. So we'll look at the scalar and vector forms of a surface integral. So the first one's called a surface integral for short, and it's really just it's a scalar surface integral, and it's a bit like before. So we're basically summing over a function, a scalar function over a surface. And because surface has two dimensions, it's a double integral. That's how we write it down. If f was 1, this function was 1, that would just give you the surface area, which is a common application. If f was, say, if this was a surface which was a really thin surface, and the f was the density of it at any point in time, then this would give you the mass of the surface. So a bit like we did massive laminas earlier. So that's some applications for it. We won't use this one very much, and I'll show you how to work some of them out in general a bit later on. But for the moment, the main way I want to do it really is just to know that if you've got f equals 1 surface area, that's the main thing I want to use for the moment. So that's a surface integral. So the one I really want to concern about, the one I want to focus on is a flux integral. So just explaining a few things. So how the flux really works is at any point in time, so my vector field F, I want to consider the component of the vector field in the direction of the normal. So I want to take the dot product of it with the unit normal to work out how much is actually flowing perpendicular through the surface. I don't care about parallel on the chords, I want to know perpendicular. So F dot N is the amount of stuff flowing in a single point. That really is the flux at a single point. And I want to add that up across the whole surface. So the flux the total flux would be a double integral of f dot n across the whole surface. And so for short, how we write that down is write this as f dot product with ds, and I write it s as a bold. So the ds suggested it's a vector form of a surface, a vector surface. So that would suggest that it's not just a surface, but it's orientated surface with a certain direction. The little squiggle underneath suggests it's got a direction to it. And so you can see how I write it in print. So you can see that when I've got a squiggle underneath, I would bold. So F and S are bold. So that's sort of so the first one here is sort of the definition. The way to work it out in practice often is the second form. Now you can actually write it down as this sort of form. So just like if you remember, we've written out vector line integrals as integral of p dx plus q dy, sort of idea. Well, you can do the same thing here. It's just the different components of f with respect to the different things. Now that's not quite right. How to fix up that writing? That should be a z there. That looks better. So this last form here, although I've corrected that, it tends not to be very useful, unfortunately. So although I've written it down just to give the similarities between everything, this isn't very useful because you have to work at each of these parts for each section of it, and you have to worry about orientation. Orientation is really critical when you've got a vector integral, so vector line or vector surface, so flux integral. The orientation is really important, and this formula here is really good if it's orientated, pointing in the positive x, y, and z direction, not a problem. But if you've got a surface which the orientation changes as it goes around, you can easily get the wrong answer from this approach if you're not careful, because it doesn't take into orientation very clearly the notation down. Well, the other sort of forms are a lot more careful with that. So I wouldn't encourage you to do this form in general. It works nicely if you've got boxes, like if the surface ends up being a bunch of planes, then that's not too bad. But if it's a more of a curved sort of surface, bends round, then you can easily go the wrong direction with that sort of formula. So let's talk about how to calculate any of these. So I haven't really talked about how to calculate surface or fluxes directly. So the way to do it is we'll have some more powerful theorems called Stokes' theorem and divergence theorem, which help evaluate flux integrals in special circumstances. So when there's special circumstances apply, they are really helpful. So we'll do that next week. Then it depends. So I want to talk about simple cases first. So some simple cases is when the amount of surface area really is just a bit of a plane, and so we can write it as just a bunch of normal area, which we can write as say dx dy or r dr d theta. So the normal just basically consider it just like a straight normal double integral. That's a nice simple case. So bits of planes, which is what we'll do first. Other easier cases is when the unit normal is pretty easy to work out from geometry. So for a plane, you can just see it. I know what the normal is just from normal geometry sort of things. So they're the easier cases. Harder cases is when the surface is really generally curved and it's not easy to work out what the normal is, and you have to fall back to some other approaches, which I'll mention later. So you can always work them out. So let's work it out in this particular case. So the flux in this instance really is the double integral of f dot n d summing up over the surface area. And really, let's put into something here. It's summing over my little rectangle. So f here is minus x minus y minus z. And my unit normal, because it's a nice rectangle, easy to see, I can say, oh, that's just the normal here is 0,001 ds. And if you take the dot product, you can see lots of things simplify because you've got lots of zeros there, and you're getting minus z ds in the end. Now, a few things here is I've got to try to evaluate this sort of stuff. First thing is DS. It's just a bit of a plane here, and so a bit of DS is just a bit of the area. You go, well, each bit of area is just a small section with different x and y values. So I could write that down as dx dy. So because it's a bit of a plane, I just work out what the two different variables are changing my plane, and they'd be the two differential operators. So I really just convert it to a normal double integral, which I can do quite happily. And I can write down the limits here if I wanted to. X is from 0 to 2, y equals from 0 to 3 are the two different, see from my little base here, my shadow I should say, my shadow, you go what the actual different letters are, what the different limits of x and y are. But as you go, hold on a sec, I've got a z here when all my variables x and y. So what I really have to do is I have to convert my z back in terms of x and y. And the way to do that, just look at what the surface is. You go, well, what's the surface? So the surface is at the top, and you go, oh, bang. That's pretty nice, actually. For my surface, z is equal to 4. It's just a constant. So in this special case, at least, my z is minus 4 dx dy. And then you can do this integral normally. That's fine. Just want to show you some tricks for it, though. I can factorize the 4 out. So it's really just the double integral over my rectangle still of ds. Or I can write as a double integral as I did before. But this double integral ds, that is just the surface area. So that's going to be the surface area of my rectangle. So instead of actually working out all these integrals directly, noticing some special features is actually helpful. Now, surface area of a rectangle is easy. That's just the area of a rectangle. So the area of a rectangle would be the length times by the breadth. So 3 times by 2. And if you multiply all those out, you're getting minus 24 as the answer. So the amount of flux of the vector field through this particular rectangle ended up being minus 24. And as we thought before, we thought it was going to be minus. So we got the minus sign right. The magnitude we just couldn't work out from the picture alone. But that's sort of way of working it. So that's a simple case because it's a plane parallel to one of the standard planes. And so you can always convert ds into just dx dy quite easily. But you can see other tricks is when you're doing those things, you need to, if you've got z equals a constant, you can use that to great advantage to yourself. That's a simple case. Let's do another simpler case. Okay. And then I'll go a little over a longer one. So, let's draw a picture. So I've got a sphere. It's all sort of sphere, center at the origin, and a length 1. And you can write it down. You can write the equation of this sphere several ways. So essentially, it's x squared plus y squared plus z squared equals 1. For short, just to make the answer easier, you can write it as the length of bold x squared equals 1. That's where bold x is just a way of saying the position vector anywhere. All right, so that's just this. I've got a sphere. That's my little surface I've got. I'll just consider some various points. If you happen to have a charged particle of length of with a charge of q in the middle here, then you have an electric field. And if it's a positive charge, then the field is really strong and pushing away, but it gets weaker as it goes further away. And this is what the vector field is. Q is the charge. You know what pi is. This epsilon 0 is the permittivity of free space, which is some special constant from physics. How would we leave it like that? Um, I think that's a good name for it. So it really is just some special constant from physics. So this is called Coulomb's law. So this is a key theorem in physics. I guess that's what's the key result of it. So this describes how the electric field around a charge at a single point. What I want to know is what's the total flux through this surface I've gone. So I've just done a little box around it, so a sphere. What's the total flux through that? And that's called Gauss's law. So I've got one key rule, and working this total flux gives you another key rule of physics. So just trying to, it just ends up being an example, but I want to just show you that some of this idea of flux is actually really useful in various applications. That's why I picked this example. I probably picked it in the study guide for similar reasons, but just want to show it to you. So the flux then would be basically work at the flux, so it'd be E dotted the unit normal at every single point and summing it over the entire surface. So I've got to do a few things. I know what E, that's the electric field. That's the measure of electric field. I have to work out what N is. So N's the unit normal. So if you think about any point on my surface here, the normal, I've got two choices. They're going to be pointing outwards or inwards. So let's just pick one direction. Let's make it an outward orientation. So let my normal picking point outwards. Because of how a sphere works, at least it's nice and easy to work out, is that the normal is pretty much just sticking in the same direction as it is straight from the origin. So it really is, for any x, y, it's just the direction it is from the origin, which we write as x, y, z, or x tilde for short. That's really just the normal. Well, that's the direction of the normal, I should state. And then we just need to divide through by its length to get its, and make it a unit normal. So let's write, so the electric field dotted N then is this constant at the front, some mysterious constant at the front, times by x, the length of x, cubed dot product with x tilde on the length of x. So I still have this constant. That isn't going away. To x dot x, that's the dot product of x with itself. That would give you, if you work it out, x squared plus y squared plus z squared. But that's just the length squared. So that actually ends up being the length of the vector squared. And the bottom ends up being, I've got cube of it, one of them, so I've got the length to the power of 4. Until you get a bit of cancellation. So all those disappear, and you get 2 on the bottom. So it ends up being this constant of 1 over the length squared. But on the sphere, at least, so on this particular sphere, well, the constant is not changing at all, of course, but the length of this vector, we know the length squared of it is a 1. That's what the definition of the equation of the sphere is. So that ends up just being 1. So you can leave it all together. So as a matter of fact, this E dot N just reduces down to a constant in this particular case. This is a very nice situation, really. So the flux then is the double integral of this constant respect x, and it's a constant, so I can just factorize it fully out of the integral if I wanted to. So it ends up being, the flux is this integral of the double integral of across the surface, which is end up being the surface area. So whenever you're getting a double integral over just of bits of surface area, that will give you the total surface area from the entire sphere. Here's the question for you. Does anyone remember what this is? A sphere of radius 1. What is the formula for the surface area for that particular sphere? Anyone remember? circling the rest of the bits down while people might have a go at it. And remember the surface areas for a sphere. Someone's having a go. Good on you. So in general, it's 4 pi times by the radius squared is the surface area. That's it. So the surface area in general is 4 pi the radius squared. The volume is 4/3 pi r cubed. That's the volume. They're related. If you take the derivative of the volume, you get the surface area. So yeah, so 4 pi is the surface area, and if you notice the 4 pi's cancel out, which is why the 4 pi's in that formula, and you're getting the charge divided by the permittivity of free space. And so that's what the flux is. So this is the electric. So this is the electric flux. This is how much the electric field is flowing through this sort of region, and that's called Gauss's law. And this permittive, and so if you start talking about how this changes in time, then you can work out the speed of light. So this is one of Maxwell's equations, and he used this to estimate the speed of light. So this epsilon here, if you use this one as well as the, I can't remember what it's called anymore, you can work out what the speed of light is. So this is related to speed of light. So that's what Maxwell did. Yeah, so that's an example of another easy case. So this is easy because the unit normal at least can work out from geometry, and it just happened to fall out. So you're going, well, so we've been lucky so far of getting easy cases. What happens if you have a case where you can't just write down ds as something like dx dy or something like that, or if the unit normal gets really difficult to find out, how can you actually work things out? Well, you really just have to fall back to parameterization. So that's always the fallback procedure. And so I know we're just about to hit the hour mark, so I'll just do one more example. So because I'm running x all over the place, I'm going to write, instead of writing the vector x, y, z, I'm going to write it as a bold r in this case, just because I want to use x and y as the parameters too. And you can get really confusing how writing it down at times. It gets confusing one way or the other. Notation's not perfect, but try to do it capital R. Okay, so harder cases, we really need to parameterize the surface. Now, because it's two-dimensional, normally you have to parameterize in terms of two parameters, so u's and v's. If it's really difficult, you might have to split it up into two different pieces even to parameterize each both separately. So they're called charts. You might have to have multiple charts for it to work. So how you work it out is, first of all, you work out a normal, not the unit one, but it's a capital N. And basically you get your vector, you take the partial derivative with respect to u's, because in assuming where you work out a function x, y, and z in terms of u's and v's, you take the partial with respect to u's, then do the same thing, take partial with respect to v's, and then take the cross product of those two. That gives you this capital N. Now, it's a normal. We don't know it's supposed to be pointing up or down. So there's two possible orientations for it. So therefore, I've written plus or minus. You actually have to think carefully which one of those two it is. And that's any place mistakes that people make. For the formulas, I'll just write down positive sign. So formulas are lovely things. You just by swapping the roles of u's and v's, you can make them more positive. But that's a bit of a cop-out. You have to look at it carefully. And so I'll just write down positive for the moment. So that's what capital N is. Now, it's not the unit normal, but you could easily make it by just dividing by its length. But this vector is useful for a few things. If you take the length of that vector, that tells you the surface area for a little, tells you what the surface area for a little small snippet bit is. And so we can use that to work out a surface area integral. So not quite written so clearly, so how will I do that down? So to work out a scalar surface integral, so a function of x, y, and z ds, then I basically plug in, replace f by making it into a function u's and v's. So just basically all I'm doing is just plugging in replacing x, y, z's by expressions of u's and v's, then multiplied by the length of this n vector I've just worked out. As I said, that's the length of RU cross RV times by dA. And in practice, that would just be du dv or dv du, one of the two. So that's what it's going to look like. So any particular surface integral by parameterization, really just integration by substitution effectively, ends up being the length of this capital N you've worked out du dv. And that really, what that does, effectively, it just converts it to a normal double integral, which we know how to do. Well, in theory, know how to do. Sometimes integrals can be quite difficult, but that's the basic process. So that's how you can use this capital N to work out any scalar surface integral. You can also use it to work out flux. So the flux, so d bold S, really is this normal vector dA, and as I said, dA is something like du dv or dv du, one of the two. And so any old flux integral over here, sorry, if you give my cursor. So a flux integral finally better. So a flux integral can really be thought of as f dot bold N du dv. Now, as I said, you have to worry about the sign. So N might be plus or minus in reality, but you have to be careful with it. Now, that's what it is in general. For the special case, if you got the standard parameterization, just parameterizing, say, z in terms of x's and y's, that's a very standard case, then capital ends up being this sort of much simpler form. So plus or minus, minus zx, minus zy. So they're the different partial derivatives at 1. So that's a much simpler case. And you really use the third component, which has got a 1 there, to work out if it should be using the positive or minus sign. That's how you do it in practice. So that's the simpler case. So that's what it is in full generality. We'll just stick with the simple one for the moment. Let's do an example just to get a sense of how it actually works. Okay. And then I'll finish the main thing I want to talk about. So I've got a x, y, z. So back to our quartic surfaces we did ages ago. So I've got a paraboloid, which looks like a bit of a hill. So I've got a paraboloid of z is equal to 4 minus x squared minus y squared. I'm assuming that the surface is oriented downwards, which means the normals, wherever they are always pointing and will look like inside the paraboloid effectively. I've got it situated so it's just the part of paraboloid sitting above the xy plane. That's my basic picture. I've got a certain vector field, f, which is the constant one. So it's just pointing, all the arrows are pointing. Wow, that's really hard to draw. I try to say this way, but really difficult. So I haven't drawn it very well to be able to draw the vector field. So it's coming out sort of right out of the page, right out of the screen for you guys. And right towards us all the time. It's as I've drawn it. So I don't know, put a bunch of dots. That might be a good idea. So therefore the vector field's coming right at us, like a bunch of arrows shooting at us. So what we have to do is I want to try to work out the total flux through the surface. So as you can see that on the far side of the paraboloid, some of it's going in the same direction as the normal. On this side of the paraboloid, some of it's going in the opposite direction, and they'll cancel out. So we're looking at the net flux, so to speak. And so you can see some going in, some going out, so some will cancel out. And so it may not be immediately clear what the answer is intuitively in this case because of the cancellation. Overall, though, because there's a component of flux that's going up and that's going the opposite direction to all these down arrows, the net flux is going to be negative because the IJs, lots of that will cancel out. The K component is really in the opposite direction. So we'll have a net negative flux as the answer. That's the intuitive way. Let's do it in practice though. You look at it and you're going, well, this isn't easy because it's a curved surface, so it's not much of a plane, and I can't even work out the normal that easily for that matter. So what I really have to do is I really have to work out this capital N business that we're just talking about. Now, in a simple case, so not the simpler case is when I can parameterize the surface in terms of x and y's, which I've got. So z is equal to x and y's. So in that case, then this capital N is either plus or minus, I'll work out which two it is in a second, of minus zx minus zy 1. Yeah, well, okay, at least I can do that simple one. So let's work them out. So z here is 4 minus x squared minus y squared. Let's make sure you're not asleep. What is zx equal to? And what's zy equal to? Let's work at these partial derivatives. Let's see what I've got still on the line. Thanks for staying, by the way. I'm going slightly over time, so you're getting minus 2x for the first one, as Bill said, and so minus zx would be positive 2x, and as several would have said, that zy is minus 2y, so minus zy is positive 2y. So capital N then is either plus or minus 2x, 2y, 1. So it's one of the two options. Which of the two options really just depends on the orientation. So I've either picked, I can pick the orientation to be in, pointing down or pointing up. They're the two choices. So if you look at this one here, the arrow, let's just pick the one at the very top. That looks the simplest one to describe. You can see the normal is supposed to be pointing down, so it should be a negative k version. So therefore, for it to work, where it says 1, that's got to be a negative sign for it to really match up. So in this particular case, the one I want is the minus case. So it should be minus 2x minus 2y minus 1. So it's got to be always pointing the down one. And so if I pick the upwards orientation, it'd be the positive version of it, and you get the. And so you can appreciate the answer would be almost the same because it'd be a minus sign difference. So it's just a sign error, but that's important to take thoughtful of. So the flux integral end up being is basically summing up f dot capital N over the parameter space, the xy space. So I really over the shadow of this particular parabola. So just summing up this over the shadow. So let's work this out. So f here is 1, 1, 1. Dot product with minus 2x minus 2y minus 1. So you get the dot product, getting minus, it just ends up summing all the things up. And so the flux then is summing up over the shadow, which we'll call B for base, of this expression. dA. And I reckon dA here can either be dx, dy, or dy dx, etc. I mean, we can pick either of whatever's more appropriate at a given time. But I write dA for short. My writing might be a bit neater. So let's have a look. We have to work out what this base really is for a start to help us out. So the base here really is the shadow of the paraboloid makes. So it's the all the xy values that sit below this paraboloid. So you can see it's a circle, so that's the base. And that's just going to be the circle. And if I look at it, when z equals 0, you get 4 minus x squared minus y squared equals 0. So that's the outside of it. So the base here really is x squared plus y squared is less than or equal to 4. the base here is a disk, so integrating over a bit of a circle, really, of this particular thing. So it's a double integral integrating over a circle. So how do you think you'd do it? So what approaches would you do to try to answer this question from now on? So we've converted a flux integral over a whole entire surface to release a double integral. And so, as someone's suggesting, there's more than one choice. One option is, if you're just doing it directly, polar coordinates would be the way to go. And so, and what I would write there is that day A would be r dr d theta, for example, and x would be r cos theta and y would be r sin theta. And you could do polar coordinates. That's fine, and it works quite nice, and it works quite quickly. I'm going to do a slightly different approach, just to show you some other things you can do. But polar coordinates, nothing wrong. I'm going to split it up. So I've got minus 2 the double integral of my circle x dA, minus 2 the double integral of x, y dA, minus the double integral of over the base dA. So that's another way of writing it. All I've done really expanded this sort of thing out. Now, a few things to notice. This double integral dA is really just going to be the area. That's going to be my area of my circle, which I can easily work out. And so that's going to be pi the radius squared. And the radius is 2. So that's that bit I can work out quite nicely. The double integral of x dA, that's related to the x coordinate of the x coordinate of the center of mass. In particular, if I divide it by the A area and multiply it by the area, so just make sure I don't cancel out, this bit here then would be the x coordinate of the center of mass. And similarly, if I check an A on an A, this thing here, so the double integral of y dA over A, would be the y coordinate of the center of mass. But if I draw a circle, so I've got my little circle here, the center of mass of this circle would be, well, it's nice and symmetric. It's going to be bang in the middle here. So the coordinates of the center of mass would be the bang in the middle, would be the origin, and so it's going to be 0 and 0. And so therefore, I can 0 minus 4 pi, and so the answer ends up being minus 4 pi in this case. So that's a different way of doing it. So you can use some of the applications of coordinate center of mass and area to try to simplify some things. Now, polar coordinates would have got it for you fairly easily too, of course. But just trying to show other ways which might be helpful. Certainly, recognizing area is a great time saver. Center of mass, only works really nicely on simple objects like circles and triangles and things like that. Not so for more complicated ones. So that's the main theory I wanted to cover. I mean, I didn't do a super hard case where the parameters U's and V's are something other than X, Y's, but it's the same sort of approach. So the push I really want to cover in this subject, though, is not getting bogged down in the really tricky situations, but try to look at some of the higher level theorems. So that's why I would like to focus on Stokes and divergence theorem that we'll look at next week. That's more the thrust of it. But it's good to know how to do all the methods. I mean, it's always good to have the fallback approach. So, as I said earlier, you can now finish off assignment 3. Just that covers the curl and divergence only. And then once you've done look at curl and divergence, Stokes and divergence theorem, you can then try to do assignment 4 as well. So, any questions? Well, I've got one person had a question, which I'll cover just at the very end here. Otherwise, you guys might want to post them up if you've got any. This is tutorial 8, question 1E. You had to do a vector line integral along this curve. As you can see, this is the picture straight from the tutorial manual. And because it's a closed curve, which is the very first thing I look for vector line integrals, I think, oh, why don't I use Green's theorem? That sounds a good idea. Now, if you look at this, though, these arrows are going in a clockwise direction, where Green's theorem requires the curve to be traversed, I move around in an anti-clockwise fashion. So this orientation's round the wrong way. So just like for surface integral, orientation is important. It's true for vector one, so it's true for Green's theorem. So in order to use Green's theorem at this, the first thing I need to do is just swap the direction. I just need to change the arrows and make the arrows all the opposite direction to make it anti-clockwise. The implication of that makes it negative. So you'll get the negative of what you would otherwise get. Then you can apply Green's theorem. Green's theorem, if you keep going, would give you end up being 1, I think, in this case. And so the original answer would be, because the opposite direction would be minus of that. So -1 ends up being the answer. So just mention that one because I think it's a good question. That orientation really is critical for these things. You have to take careful attention to it. Now, most of the time, by default, if orientation is not mentioned, we just use default ones. For curves, closed curves, we assume they go around anti-clockwise. For closed surfaces, we assume outward orientations. They're sort of the default things we consider to make some things nicer for us. But if things are different, we need to pay attention to it. So thank you guys for sticking around. It's 15 minutes over. But I think it's good just to have all those variety of examples. I didn't want to throw a really difficult one into you without doing some simpler ones. What I thought was simpler, I hope. So there is levels of difficulty, as you can see here, and so step yourself up. But please be assured that the focus of the subject is on what we're doing next week, which is the more high-level ones. But to understand them, it's good to be able to handle some of the nitty-gritty bits. So do you guys have any questions just before you have to head off and to work or whatever you have to do? If not, I will finish it there. So thanks for answering a few questions. That's very helpful. It's good to keep thinking through stuff. All right. Okay. Thanks, guys.